Ammonia will be used in the laboratory in major quantity, so that will be produced by the Haber's process. These are stoichiometric hydrates which will be formed by S block elements which are highly electropositive in nature. How many number of electrons should be present? That many number of electrons will be present in the structure. This palladium and platinum absorbs hydrogen gas more, so it will be act as storage media. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up session 2 from the chapter Hydrogen. In the last class we have seen or we have discussed about occurrence in nature of hydrogen, position of hydrogen in the periodic table, resemblance of hydrogen with alkali metals, resemblance of hydrogen with halogen family, and the dihydrogen preparation we have seen. In this class or in this session we will discuss the physical properties of dihydrogen and the chemical properties of dihydrogen, uses of dihydrogen and the hydrates. What are hydrates? What are the classification of hydrates? We will see in this session. First, the physical properties of dihydrogen. Hydrogen is a colorless, odorless, tasteless gas. Its density is the lowest of all chemical elements, that is 0.0999 gram per liter. Means it is odorless, like smellless or tasteless, colorless, and it is a gas. Its density is completely low comparing to of all elements. By comparison, a liter of air weighs 1.29 gram, 14 times as much as a liter of hydrogen. 14 times if we add hydrogen to a common air, that much one part of 14 will be the hydrogen mass. Hydrogen changes from a gas into a liquid at a temperature of 252.77 degrees Celsius and solidifies at a temperature of minus 259.2 degrees Celsius. Hydrogen changes gas to liquid at temperature minus 252.77 degrees Celsius and solidifies at the temperature 259.2 degrees Celsius. It is slightly soluble in water, alcohol and few other common solvents. Next, chemical properties of dihydrogen. We will see the first reaction with halogens. Dihydrogen combines with halogens to give hydrogen halides. The reactivity of halogen towards hydrogen decreases in the order. See here, fluorine, next chlorine, next bromine, next iodine. So, fluorine, hydrogen and fluorine at the dark reaction, hydrogen, fluorine will form. Next, hydrogen and chlorine diffused sunlight, in the presence of diffused sunlight, HCl will form, hydrochloric acid. H2 and bromine, that is Br2 at 673 Kelvin, HBr, hydrogen bromide will form. H2, that is hydrogen and iodine at 673 Kelvin in the presence of platinum catalyst, it will form hydrogen iodide. What they told? Dihydrogen combines with halogen to form hydrogen halides and its order is first in the increasing order fluorine, in the least order iodine is present. Next, reaction with dioxygen. Hydrogen reacts with dioxygen to form water. The reaction is highly exothermic. Exothermic means the heat will be evolved, not involved. Heat will be liberated from the reaction. So, when hydrogen or dihydrogen reacts with dioxygen, it will form water. That reaction will be exothermic reaction. See here, H2 plus O2 both are in gaseous state. In the presence of catalyst or heating, it will form H2O, that is water. Here, the exothermic reaction enthalpy is minus 285.9 kilojoule per mole. Next, reaction with dinitrogen. Hydrogen reacts with dinitrogen in the presence of iron catalyst at 673 Kelvin under a pressure of 200 atmosphere pressure to form ammonia. This is used in the manufacture of ammonia by the Haber's process. By the Haber's process, the ammonia will be formed when dihydrogen will be treated with dinitrogen in the presence of iron catalyst at 773 Kelvin and 200 atmospheric pressure will be used. This is ammonia, NH3. Next reaction with metals. Dihydrogen combines with many metals at high temperatures to yield the corresponding metal hydrates. If dihydrogen is reacted with metal, it will form metal hydride. M is a alkali metal like sodium, potassium, rubidium, like that. Reactions with metal ions and metal oxides. Dihydrogen gas reduces some metal ions in aqueous solution and oxides of metals into corresponding metals. See, hydrogen gas treating with palladium. In the aqueous solution, it will form palladium and hydrogen ion. Okay. Here also H2, that is hydrogen, Mx, that is metal oxide, it will form metal plus water. Next one, reaction with organic compounds. Dihydrogen reacts with many organic compounds in the presence of catalyst to give useful hydrogenated products. Example, hydrogenation of vegetable oils using nickel catalyst gives edible fats, that called vanaspati ghee or margarine. Okay, if oil is getting hydrogenated in the presence of nickel at 180 degree Celsius, it will form fat. Next, hydroformylation of alkenes gives aldehydes which further under reduction to give alcohols. Here hydrogen is treated with carbon monoxide and alkene. What it will form? Aldehyde will form. If that aldehyde again reduces means hydrogen should be added, that will form alcohol. This is alcohol. First aldehyde, then later reduces to alcohol. Next, uses of dihydrogen. Those were what we saw, physical properties and chemical properties of dihydrogen. Now we are discussing about uses of dihydrogen. It is used in the production of ammonia by Haber's process. Ammonia will be used in the laboratory in major quantity, so that will be produced by the Haber's process. Hydrogen is commonly used in power stations as a coolant for the generators. Okay, in the power stations, hydrogen gas is mostly used as a coolant. Used in the manufacture of vanaspati fat by hydrogenation of vegetable oil. This reaction also we saw. The largest application of hydrogen is for the processing of fossil fuels. To process the fossil fuels, hydrogen gas is very much needed. Hydrogen is used as a shielding gas in welding methods such as atomic hydrogen welding. It is used as a rocket fuel in space research. Hydrogen gas will be used as rocket fuel. This is the major applications and the overall uses of dihydrogen. Hydrogen is used in the manufacture of methanol, alcohol. Stars use hydrogen as a fuel with which they produce energy. Direct reaction of dihydrogen with chlorine is used for the preparation of hydrogen chloride. H2 plus Cl2 will form 2HCl. This reaction also we have seen. Dihydrogen is used in the manufacture of metal hydrates. In the metallurgical processes, it is used to reduce heavy metal oxides to metals. Hydrogen is used as a fuel in space rockets and guided missiles. The overall uses, if you see, hydrogen is mostly used for our many uses like oil, like fuel in the rocket science. From the least part to from the application level, the uses of hydrogen we can see. Next is hydrates. Binary compounds of hydrogen are known as hydrates. Binary compounds of hydrogen. Two compounds of hydrogen will be called as hydrates. If E is the symbol of an element, then hydrate can be expressed as EHX. For example, MgH2. E is the symbol of an element, this is H, this is X. Or EmHn, that is B2H6. Hydrates are broadly classified into following three steps: ionic hydrates or saline hydrates, covalent hydrates or molecular hydrates, metallic hydrates or non-stoichiometric or interstitial hydrates. These are the three hydrates which will be classified from the hydrates. Okay. First we'll see what are ionic hydrates. These are stoichiometric compounds of dihydrogen formed with most of the S block elements which are highly electropositive in character. These are stoichiometric hydrates which will be formed by S block elements which are highly electropositive in nature. Electropositive nature means it tends to lose its electron for the electron deficient species. Elements of group 1 and 2 except lighter metals like lithium, beryllium and magnesium form ionic hydrates. Ionic hydrates are also known as saline hydrates or salt-like hydrates because their properties are identical to salt. It will also call it as saline hydrates or salt hydrates because the ionic hydrates will resemble the character of salt. In ionic hydrates, hydrogen exists as H-. For the hydrates of group 1, general formula is MH, where M represents sodium, potassium, rubidium, cesium and francium. Okay. Examples NaH, KH, rubidium H, etc. For the hydrates of group 2, generally formula is MH2, where M is represents as calcium, strontium and barium. Example CaH2, that is calcium hydrate, strontium hydrate and barium hydrate. Next is covalent hydrates and or molecular hydrates. Elements of group 13 to 17 form covalent hydrates. They possess covalent bond in their structure. We have seen what are covalent bond, what are ionic bonds, what are the properties of both the bonds, everything we have seen. Now in hydrates we are correlating. For example, BH3 like boron trihydrate, aluminum trihydrate, methane, ammonia, H2S, water, hydrochloric acid. Like this the covalent bond will be there. Note, hydrates of groups 13 and 14 are neutral. Hydrates of group 15 are basic. Hydrates of group 16 and 17 are acidic. Molecular hydrates are further classified into 3 types according to the relative numbers of electrons. And in their Lewis structure. Based on that, electron deficient, electron precise and electron rich hydrates have been classified. Electron deficient hydrates have less number of electrons in them required for to writing the conventional Lewis structure. To write Lewis structure, we will represent by valence electrons of the element. Electron deficient means that much electrons whichever we have to predict there, that many electrons are not present, that is deficient electrons hydrates. All elements of group 13 will form electron deficient hydrates. For example, B2H6 diborane, they act as a Lewis acids, that is electron acceptors. Electron precise hydrates have the required number of electrons to write their conventional Lewis structure. All elements group 14 form electron precise, that is methane, which are tetrahedral in geometry. Precise means how many number of electrons should be present, that many number of electron will be present in the structure. Okay, for example, methane overall is group 14 elements. Electron rich hydrates have excess electrons which are present as lone pairs that will form by element of group 15 to 17 form such compounds. Electron rich means more than required for the bonding or more than valence electrons it will be present and it will act as a lone pair. Example, ammonia has one lone pair, H2O2 and HF, 3 lone pairs are present. This is about electron deficient, electron precise and electron rich hydrates. They behave as Lewis bases, that is electron donors. The presence of lone pairs on highly electronegative atoms like nitrogen, oxygen and fluorine in hydrates result in the hydrogen bond formation between the molecules. This leads to the association of molecules. Whenever more electrons or lone pair electrons are present on the element, it will act as a electron donors or electron bases. Presence of lone pairs on the electronegative atom leads to the hydrogen bond formation between the molecules. This leads to the association of molecules. Note, due to the higher electronegativity of nitrogen, oxygen, fluorine, the magnitude of hydrogen bonding in their hydrates will be quite appreciable. Okay, due to the higher electronegativity, the hydrogen bond formation will be favorable. Hence, the boiling points of ammonia, water and hydrogen fluorine will be higher than that of hydrates of their subsequent group members. Phosphorus cannot form pH5 due to high enthalpy of atomization and high electron gain enthalpy value of hydrogen. Next, metallic hydrates or non-stoichiometric hydrates. These are the hydrates of transition elements. Transition elements means D block elements except elements of group 7, 8 and 9. And inner transitional elements also it will include. In transition elements, there are small empty spaces between the atoms called interstices. In the D block also, there are so many gaps or empty spaces are there that will be called as interstices. Hydrogen gets absorbed in these empty spaces to produce non-stoichiometric hydrates or interstitial hydrates, which are known as metallic hydrates. In that gap or in that interstices, the hydrogen gas will be get absorbed. There it will form non-stoichiometric hydrates or metallic hydrates. Okay, these are the examples: nickel hydrate or lanthanum hydrate or vanadium hydrate, like that. The property of adsorption of hydrogen gas on transition metals is widely used in catalytic reduction or hydrogenation reactions for the preparations of large number of compounds. This absorption or adsorption on the metals or transition metals will be used as a major application process called catalytic reduction or hydrogenation. Some of the metals like example palladium and platinum can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This palladium and platinum absorbs hydrogen gas more, so it will be act as storage media. This property has high potential for hydrogen storage and as a source of energy. Here note, hydrates of beryllium and magnesium are known as polymeric hydrates. In polymeric hydrates, a large number of units are joined together by hydrogen bonding to produce a long chain of beryllium hydrate or magnesium hydrate. Okay, that is polymeric hydrate. Till this, we have seen the various kinds of hydrates. In this next session, we will see about water, physical properties of water and chemical properties of water. I hope you have understood whatever I have taught today. So, we will meet in the next session. Thank you.